All right. For those that have missed my lecture on integration, introduction to integration, um, I'm going to go through the initial stages of what is integration. For now, we've done differentiation, so we understand very well. Uh, Integration is just the reverse process of differentiating. So we are going to stick to standard facts without getting much into the proofs because most of the things anyway they are given in most exam you can do most exam papers you can do for mathematics, be it at university level or at college level. So we are going to look at most of the stuff that says you should be able to integrate standard mathematical functions including trig and exponential functions, and be able to use the reverse chain rule to integrate functions of the form f of x plus b. I think they're just saying here, we'll be saying the integral of f prime of a x plus b dx should be just equal to 1 over a f of ax plus b. So you can actually treat it as a formula as well. Using trigonometric identities in integration, that's one important part. So you got to remember most of the trig identities, and most of the trig identities anyway are tied to the Pythagoras theorem, which says cos squared x plus sine squared x is equal to 1. Then you should be able to use the reverse chain rule to integrate more complex functions. We will get to that point of differential equations later on through the course, but that's the primary objectives of integration. So we've got standard functions of integration. The first one, which is basically the rule of integration. You normally don't find this anywhere. So you should just know if we are integrating, we do the reverse of differentiation. Remember, if y is x to the power of n, I've proved this in my previous videos, dy over dx is equal to n x n minus 1. So you can try to see that, you can see the process is you're reversing, so it's n minus 1, that's why we've got n plus 1 here, and we are adding there as well. We multiply n here, so we divide there. That's basically the idea. I've proved this already. The proof use what? First principles. Together with the binomial expansion, of course. That's basically the definition of integration. It is the reverse of differentiation. The standard proofs, if you check my videos, you know that the integral of the derivative of e of x remains e of x. Hence, the integral of e of x will also be e of x. And the derivative of natural log of x is 1 over x, so the integral of 1 over x is just natural log of x. Of course, the absolute value of x, because we understand that just to define it in terms of functions, this is the function natural log of x, and it is defined over the domain that says x is greater than 0. It's going in this direction. So it's most advised here, unless in the questions you're dealing with, the domain itself is specified to be positive, then you know that you can leave that and say natural log of x without putting the modular sign. That's one of the things that are very important at this level of mathematics. Again, you're going to need to integrate these standard functions. Since we have done the proofs of why the derivative of cos x is minus sine x, and the derivative of sine x is cos x, you can also see, treat this as formulas, you can also see that the derivative of cos x, the integral of cos x is sine x, and the integral of sine x will be minus cos x as well. We have done the derivative of tan x as sec squared x using the quotient rule. That's the basic, easiest way to do that. So the opposite is true. The integral of sec squared is also equal to tan x. However, just to remember again, These are the most important functions in integration because they're kind of a bit untidy, complex in nature. You can prove them by various numerical methods to say why is the integral of sec squared equal to tan x, why is the integral of cosec x cot x equal to minus cos x as well. You can prove that. There is so many ways to do that. I can give you one just to say, if I want to find the integral of sec squared x dx, which we know is tan x plus c. Some of you may say, why are you making this substitution? I'm working with the answer here. I can just start by saying let u is equal to tan x. I've posted a video on the importance of substitution in functions, even though it relates more to university content, but it's mathematics anyway. It defines the importance of why do we resort to substitution when we want to simplify complicated functions. So this is one way, and we know that du over dx will be equal to sec squared by the quotient rule. This also tells us that du over sec squared x is the same as dx. So we've tied that. So because of that, we can change this and say the integral of sec squared x. We are using u, so we are going to change dx and put du over sec squared x. And this just reduces to the integral of du, which is equal to u plus c. But we know c is tan x plus c. Proved. So you can prove these integrals in so many ways, but I just gave you one example. But for exam purposes, whether in university level maths, you get these formulas, so there is nothing really need to worry. But it is always good to know how these formulas are generated anyway. That takes us now to the most important part. One of them is this, a very good question. Find the integral of sec x in bracket sec x plus tan x. What we can see that this is equal to. So what is important is for me to expand. So I'm going to have the integral of sec squared x plus, perhaps I need to do this, because we know mathematically you're allowed to distribute the integral function. So I will say plus sec x tan x dx. Like that. So as a result, what is our answer to that? We are going to have the integral of, if we go back here now, we will see this is the integral of sec squared is tan x, and the integral of sec x tan x is sec x. So that's the importance of that formula. So the integral here is going to be equal to tan x, and this is going to be equal to sec x. Since we are having the boundaries, we don't need to do anything. We don't need to say plus c. And then I don't have a calculator, but anyway, this looks like special angles to me, so it's going to be tan 0, substitute 0 there, plus sec 0 minus tan minus pi over 4, that's a special angle, plus sec minus pi over 4, that's also another special angle. Tan 0 is 0, sec 0 is just 1, minus, this is also minus 1, that's also minus, because that's 1 over cos, because pi is going to be, that's root 2. So your answer is just equal to 2 minus, is it 2? It's going to be 2, that's plus here, minus root 2. That's your answer. Right? Integrating questions of this form. So we know already standard integral of course is sine. So the answer should read sine. But because inside the function there is another function which is 2x plus 3, we will have to use the chain rule. So I would say it's important to see the pattern of differentiation here. So first of all, let us start by doing this one using substitution. Then we can do these other two by just following the pattern. So the substitution that we'll do here is to say let u be equal to 2x plus 3, which means you're going to have du over 2 being equivalent to dx. I think by now we're used to my way of doing this substitution. So where I got this is pretty much easy to see. So the integral, this is equal to the integral of cos, but it's no longer cos 2x plus 3, but cos u then divide times du over 2. I think for simplicity purposes, this 2 should go outside the bracket. So we are just integrating cos u in terms of u. And we know this is just half sine u plus c. Extending it back to x gives us the answer as 1 over 2 sine 2x plus 3 then plus c. Now, that's the answer. And that's the correct way of doing it. Do we actually need to keep doing these things? No. Once you understand the chain rule, it is easier to quickly solve these things without following all this substitution. So let us explain what we have seen here. What's the relationship? You can see that the integral of cos is sine. So where did this half came from? If you look at the inside function, which is 2x plus 3, the derivative of 2x plus 3 is 2. But because we're integrating, we divide. Remember when we're doing the chain rule in differentiation, when you find the derivative of the inside function, you multiply it to the outside function. So right now, because the inside function is the derivative of 2, we divide the answer with 2. And then we just write half sine x, 2x plus 3. That's the way of doing this type of differentiation, integration. So that means to find the integral of e 4x plus 1 without doing the substitution, which is the correct method, one would simply look at it and say, the answer lies in understanding what is the derivative of 4x plus 1. The derivative of 4x plus 1 is just 4. But because I'm integrating, I divide with that. That's 1 over 4. And what is the integral of e? We know that the integral of e is still e. So the answer is e, 4x plus 1, then plus the constant of integration. Right? We don't need to do the substitution anymore. Then to go to c again, you're saying the integral of sec squared 3x dx. So we know the integral of sec squared x is tan x. But because there is a 3 here, 3x, we're going to ask ourselves, what is the derivative of 3x? It is 3 with respect to x. So I'm going to divide by 1 over 3. Then I'm going to have an answer as tan 3x plus c. Otherwise, if you don't want to follow the pattern, you just have to go through all the steps of substitution and get to the answer. All right, so this is the introduction of integration, which is summarized by this formula, as you could see. Let me just go through these two examples again and conclude the lesson. If you look at it, again, I'm going to start with substitution. But what the answer of this question look like, I know already it is going to be 1 over 3 natural log of 3x plus 2 plus the integral, which is c. How? That's the question I want to answer. How? I'm going to answer it in two phases. First of all, I'm going to justify it numerically by using substitution. Then I'll attach to the functions as well. So I'm going to start by saying let u be equal to 3x plus 2, which means du over 3 is identically equal to dx. You can do that mathematics here and see how it goes, but this is basically the idea. So if we go back to the question, because we say let u, that means the integral of 1 over 3x plus 2 dx can be summarized or changed by the substitution we've made here as 1 over u du over 3. I see that there's a 3 there, which can be written as 1 over 3, the integral of 1 over u du. Because 3 is a constant number, so there's no need to worry about 3. You can just take it out of the integral sign. But again, the integral of 1 over x is known as natural log of x. So the integral of 1 over u is just the natural log of u plus c. But our function is in terms of x, so we can say x is attached to u in the sense that u is equal to 3x plus 2, then plus c. That's the final answer using substitution. So it's easy to see how the answer has been generated. Now, we did not guess the work, the answer, because we can see already this function is in the form of 1 over x. Is in the form of 1 over x, let me put in a here, plus c dx. And from the standard integral, we know that 1 over x can be reduced as natural log of x plus c. So we know that already. But so I could just, by just looking at it, I know that the derivative of 3x plus 2 is 3. So it's going to be 1 over 3 natural log of 3x plus 2 plus c. But you can justify it beautifully by going through the standard integrals, substitution method. So clearly using that pattern, I can also see here the integral, the derivative of 2x plus 3 is 2. So I'll divide by 2. Then if I integrate this whole function, I'm going to have to add a 1 to 4. Then I also divide it like this. Then I'm going to have to say 2x plus 4, plus 3 to the power of 5 plus c, which can be written as 1 over 10 2x plus 3 to the power of 5 plus c is the answer. That is all from in terms of integration. All right, I'll leave it from there and see you in the next lecture.